All right, so the 3.4 is the second to last section in the chapter. Okay, it's called exponential and logarithmic equation. So if we have an equation that needs to be solved that's got exponents or logarithms in it, then we can use one or the other, the inverse operation to solve. So we can use like bases to solve exponential equations, and we can use logarithms to solve exponential equations. And then the definition of the logarithm can also be used to solve logarithmic equations. And there's this thing called the one-to-one property, which can also be used. We'll talk about that. And then look at a couple of applications. All right. So here's the way that we can use the like basis to solve an equation. If we have two expressions on either side of an equal sign, and they have like bases, the powers can be different, but if the bases are the same, then we can rewrite that equation as just the exponents equal to one another. And generally what that means is you're going to have a variable in one of those exponents, and then that's what you're going to solve for, because the bases are not going to contain anything that's going to help you solve it. They're just going to be used to solve. So like on this one, we've got 5, base 5 on the exponent, so the 3x minus 6 power is equal to 125. Now, 125 is not the same base as 5, but we can rewrite this. We can rewrite this as 5 cubed on the right. See that? That's 5 cubed. So now they have the same base. And so we can essentially just yank those bases away. And what we got left is 3x minus 6 is equal to 3. Real easy equation to solve. Because 3x is equal to 9. When we add the 6, x is equal to 3. Yeah, it is. I mean, yeah, because once you take those bases out, it's just a basic equation. And not all of them are going to be in this type. We'll see other things. But anyway, look at B. Now, neither one of those has the same base, but they both have the potential, because remember, 8 is 2 cubed and 4 is 2 squared. So we write an 8 as 2 cubed. And then we got the parentheses. So we're kind of using that power rule there. Because what that means is that's 3 times x plus 2 with the power exponential power rule. And on the other side, it's 2 squared. So the 2 is multiplying the x minus 3 via the power rule. And then now that we got the same bases, you know, yank those out, and you got 3 times x plus 2 is equal to 2 times x minus 3. Which means 3x plus 6 is equal to 2x minus 6. And then subtract the x from the right, or 2x from the right and the left. We got x plus 6 is equal to -6, and then subtracted 6, x is equal to -12. So that's the solution. Okay? All right, sorry about that. All right, so we can also use logarithms to solve. So what we need to do in this case is isolate the exponential expression, take the common log on both sides, which means base 10, and you can also take the natural log on both sides for bases other than 10. I find that the second one is usually the more common one. So this right here. So watch. There's no way we could write this with the same base because 135 is not a power of 5 and 5 is a prime number. So we can't write that any different on the right. So this is where we need to proceed here. We're going to take the ln, the natural log of both sides. And then remember, we use the power rule to bring that x out in front. And so x times ln x is equal to ln of 134. And from here on, it's just like a regular equation because remember that ln 5 is multiplying the x. So then we divide both sides by ln of x here. And we go through example. I'll try to put in a little bit of step in there to show you what happened. But you're basically dividing this by ln of 5 and this side by ln of 5. And then you take the ln of 5 and divide it into the ln of 134, which is approximately 3.04. Okay? All right, so 10 to the x power is equal to 8,000 again. We don't have any hope of writing 8,000 as a power of 10 because it's not. If it were 10,000, we'd be able to do it, but not 8,000. So this is why we're going to use the log. Now, in the last one here, they use the natural log, but you can also use the common log to do this. So the common log of both sides. Common log of 10 to the x is equal to the log of 8,000. Now, on that left-hand side, since we've got a 10 as our base for that exponent of x, this is where the natural log is going to work really well. And we could have done this up here, but for this one, this just simply undoes that 10 to the x power, because remember, if you, this is log base 10 to the 10th power. I'm sorry, this is log base 10 with a log of 10. So those two undo one another, and you just get the x out. We looked at that in the last couple of sections of doing that. So then that x just pops right out of that. And so x is equal to the log of 8,000. This one is pretty easy. Like I said, it's tailor-made for when you have that the x in the exponent has a, the base is 10. Otherwise, use this. All right. So 3.9. So the solution is log of 8,000. Remember, and you can look it up. Just remember about this. The reason why they changed the squiggle there is because when you take it just fills up your screen. This is what we call an irrational number. So it has to be approximated to something. So watch what my math lab asks you to approximate as. So it's an approximation. The way you get an approximation is you have to name a decimal place to which you want to round it to. All right. Here we've got one, again, different kinds of bases. No way that we can do it like the first example, but we can use the ln here. If we take the ln of 3 times 2x minus 1, we can use the power rule, then to bring that 2x minus 1 in front of the ln 3. And so we've gotten it out of there. On the other side, we're doing the same thing. We're taking the x plus 1 and move it in front of as a multiplier for ln of 7. And so then what can we do? Well, multiply this through. So 2x ln 3 and -1 ln 3. And then over here, x times ln of 7 and 1 times ln of 7. And then let's see, put, and this is something like you did ask me early in the semester about Lance. You remember there was one, he was asking how do you isolate the x? Well, you got to change the size. In other words, you got to put this x ln 7 over here with that 2x ln 3, and then put the ln 3 over here. In other words, you're changing the signs. Now you can factor out an x. And then that's x times 2 ln 3 minus ln 7. And then you're dividing by this whole amount on both sides. Over here, it just gives you with the x. And then on the right-hand side, it's ln 3 plus ln 7 over 2 ln 3 minus ln 7. And again, you can do that with a calculator. Probably with this one, what I would do is just do ln 3 and then write it down, do ln 7, write it down. You can use the calculator to put that together. And if you're using the calculator, like a general calculator that doesn't have parentheses, like this one, the best way to proceed is to do the denominators first. Like, let's say, it's just a pain in the neck on a regular calculator. If you got one that's got the parentheses and all that. So 3 ln times 2 minus, I'm going to clear out the memory, and then I'm going to put that back in there. And then I'll do the top. It doesn't matter about which direction you do it there. Remember, the reason why we have to do this is just because division and subtraction are not commutative. In other words, you got to be wary of the order in which you do it. Go through that, and then you take it and you divide by what's in the memory. And 12.1. So my suggestion is just write the things down as you go, and then double check, because sometimes, and this happens to me every time I'm using the calculator, especially one that's online like this, is I'll hit something and it doesn't register, and I don't think I got it. So you got to double check it, because you can get into trouble like that. Don't think the calculator can't make mistakes. It doesn't make any mistakes in its calculations, but there's the translation aspect of putting it in. Sometimes you'll hit something and it just doesn't press. And I assume that can happen too with a physical calculator, because if one of the buttons goes bad, even with a phone, you know, type where you got the screen type press, you still can have that happen. All right, so we can also use the definition of a logarithm to solve logarithmic equations. So first of all, we would express the equation in the form log base whatever of m is equal to c. And then use the definition of a logarithm to rewrite the equation in an exponential form. So now we're solving a logarithmic equation by writing it as an exponent. And then once you do that, you can solve it for the variable pretty much like what we've done so far. All right, anybody got any questions?
So we don't have to change it around like with the, how we normally have to do, was solving an exponent, the equation, how the in 3, so we don't have to put the 7 in front the ln. We just leave it as it is, correct?
Talking about on this, or are you talking about?
Yes. Yeah. Because, you know, normally when we change it, we will have to put, you know, put it in order. So we just leave it as it is.
In order?
Mm-hmm.
Well, for this, I mean, you got, the thing that matters is, okay, this is ln 3 or minus 2 ln 3 minus ln 7, that order matters. On this side, the order doesn't matter because it's addition. So with subtraction and division, remember those things are not commutative. You've got to pay attention to the order. That's why when I was dividing and also for subtracting, like on the subtraction, I did this first, stored it in memory, then I did this and then subtracted the memory recall so we would do it in the right order. You know, if you don't do it in that order, you're going to end up with the opposite sign of the value, you know?
Okay.
It's like 5 minus 3 is going to be 2, but 3 minus 5 is negative 2. See, it changes your sign. And then the same thing happens with the division. Okay, you've got to make sure you get this in your calculator or wherever you're writing it, and then divide by this value here, because you can't do it the other way, or it's going to be the reciprocal.
Okay.
Because if you take 6 and divide it by 3, it's 2, but 3 divided by 6 is 1/2. So you've got to watch the order when you're dealing with subtraction and division, but with addition and multiplication, it does not matter because of the what we call the commutative property. They can be, you can add 2 numbers any order you want and still get the same thing. Multiply 3 times 4 is the same as 4 times 3. 10 plus 7 is the same as 7 plus 10. That's why up here, it doesn't matter what order you do these. But on these it does, because of that change sign issue. All right, so on this one, let's see what we're talking about. We're using the definition of a logarithmic equation to write it exponentially. So we've got the log base 2 of x minus 4 is equal to 3. All right, so that means, remember the way that a logarithm is structured This is your base when we're talking about the exponent. This is your power, the only thing there on the other side of the equal sign. So 2 cubed is equal to that inside right there of x minus 4. And then when you do that, well, this 2 cubed is just going to round out to be 8. This 2 cubed is 2 times 2 is 4, and 2 times 4 is 8. And then after that, it's you solve and you get 12. Now, with these, you remember how I mentioned to you that with almost all functions, the domain is negative infinity to infinity. But the exception is with the logarithm, even though it's still a function, it's reversed. The range is negative infinity to infinity, but the domain is going to have to be restricted. Now, in a general sense, you know, that input the input for the logarithm has to be positive. So like on this, we're going to see a little bit on some things. But anyway, C12 minus 4 is equal to 8. So when we take the logarithm of it, see, it works. But if you did this, let's just say we put in a negative 8. Let's say that was 4 minus 12. Again, the order matters. So you try to put a negative number in there, take a logarithm of it. See, it's an invalid input. So that's why it's important that these are checked. In other words, the range, the domain is going to be x minus 4 is greater than 1, or x has to be greater than 4 for this to work. Greater than equal to 4. So let's look at another example here. All right, 4 ln of 3x is equal to 8. So first thing is, remember, this is multiplying this, so we can take the 4 and divide it into the 8 and get 2. All right, it's multiplying that ln. So we can divide both sides by 4 essentially. Then we got ln of 3x is equal to 2. Then the ln, so this is base ln, that means that's base e. E to this power is equal to what's inside the inputs of the logarithm. And then from there, you simply divide both sides by 3 to get x is equal to e squared over 3. And again, you got to check it, because if this comes out to be a negative value in here, then you're going to have a problem, because everything in there is going to be greater than 0. I'm sorry, greater than or equal to 0. It can be 0, but no, it can be negative. All right, so let's look at another one here. So we can use then the product rule backwards to take this, to condense this into one logarithm, because it's plusing this with the same base. So it's x times x minus 3, one logarithm, is equal to 1. All right. So again, this is the power. This is the common logarithm of 10. So 10 to the 1 is equal to the input of the logarithm, which is the x times x minus 3. Now, once you get to that point, hopefully you recognize, or here, that you got a quadratic. And the way to solve a quadratic is to set the whole thing to 0 and then factor it. So subtracting 10 to get everything on the right side, and then multiply x minus 5 times x plus 2. And then solving each one, x minus 5 is equal to 0, so that means x is equal to 5. And then x plus 2 is equal to 0, x is equal to -2. So you gotta check these, but look what happens on one of them. If you remember back, if you took 097, even if you took algebra 2 somewhere else, or intermediate algebra, or whatever they call it, you have those things, those radical equations, where you square both sides and you come out with solutions. And you really need to check those because there's a possibility that some of them won't work. Well, the same thing's going to happen here. So 5 and -2. So if we put 5 in here, then we got 5 minus 3. Well, this one's just the log of 5. And then this one is the log of 5 minus 3, which is log of 2. And then we can put it together using the power rule backwards, which means log of 10 is equal to 1. So log of 10, common log is 1, because remember, this is base 10. So that means 10 to the first power is equal to 10. So that one's all right, but watch what happens on the other side. That -2 goes in there. This is not good. All right? Because if you try to do this, even if you forget about it, it's not an input. In other words, a -2 is not in the domain. And the same thing's going to happen over here because -2 and -3 is -5. So we would have to throw out that solution. Okay? So it's important, very important, that these are checked here for what we call viable solutions. Okay? And then there's this thing called the one-to-one property. One-to-one problem for logarithms, and you can also solve with that. So what you have to do is you have to express the equation in the form of one log, and one base is equal to the same log base of another value. And then this gives us a single logarithm whose coefficient is 1 on each side of the equation. And then we use the one-to-one property to rewrite it, okay? In other words, we do what we just did in the first place, the first case earlier. So let's see how that pans out in real life. Now, we got to have one single logarithm on each side. This is akin to something else I do in 197, or something we just went over there. If you've got a fractional, what we call a proportion, it's a rational expression with just one equation on each side, you can kind of skip having to deal with multiplying by the least common denominator by just doing that cross multiplication, and that gives you the equation. Well, this is very similar, but we gotta make sure we got one equation on one side. And this is also the same thing when we did those inequalities, finding out the solution set for them. We have to have a one, when it's a rational expression, you have to have one expression, so you may have to find an LCD. Well, here, it's just that we got to do it with logarithms. All right, so ln of x minus 3 is equal to ln of x minus 23 minus ln of x plus 1. This right here on the right side, remember, these are both the same base, ln, and there's the negative sign, so we can write this using the quotient rule to condense this. So that's the ln of 7x minus 23 over x plus 1. All right. Now, because they're the same base, it's the same exact thing as over here. When you got the same base, like they did right here, you just take the exponents and equal 1. All right, except now it's with logarithms. So x minus 3 is equal to 7x minus 23 over x plus 1. And this is a rational equation, and as I was just mentioning about rational equations, generally the way you solve those is to multiply both sides by the least common denominator, which is x plus 1. So if you multiply on this side, this part goes away, and you just have 7x minus 3. But on the left, it's going to be x plus 1 times x minus 3, which is going to entail foiling that out in order to, and collecting like terms, and we're going to have another quadratic. So on this side, when we FOIL those out, we get x squared minus 2x minus 3 is equal to 7x minus 23. Subtract 7x from 2x negative, you get negative 9x, and negative 3, subtracting a negative or adding 23 gives us plus 20 there. Negative 3 plus 20. So now that's easily solved as, or factored as x minus 5, x minus 4. Setting each one equals 0, x minus 5 is equal to 0, x minus 4 is equal to 0. And so the solutions are x is equal to 5 and x is equal to 4, but we need to check them. So 5 doesn't create any issues because this 5 right here is larger than 3, so when we subtract, we get ln2, and then over here, same thing, we get a positive value for the logarithm input on both of those. And then when you simplify it down, they're both equal. Now, I'm kind of thinking that maybe this next one, no, it does check out too. So 4 minus 3 is 1. 7 times 4 is 28, minus 23 is 5. And negative minus ln of 4 plus 1 is 5. And then we can use the quotient rule to put these together. 5 divided by 5, because it's the same base. 5 divided by 5 is 1. Both sides. All right, any questions? Because we only got the application, and like I said, I got some problems I'm going to go through and that I've got from the back of the book, like we usually do. But I wanted to just
no question.
okay. All right. How long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? All right, A is equal to, remember that formula? That's the continuous compounding formula.
Yes.
That was I think it was in the first, it was in the 3.1, I believe, or 3.2. So what we're going to do is we're going to use the values they're giving us here to fill in that formula. So the amount we want to get is 3,600. Right? We want to find out how long it's going to take. The principal was 1,000. Remember, that's what that big P is. It goes out in the front. The 1, of course, is just 1 plus. And then the rate, 8%. Remember, it's got to be rate. It's a decimal. That's important. You cannot work with decimal. I'm sorry, with percents mathematically. They're for basically for expressing things because people understand percents. Whereas generally they don't understand decimals. And then, I'm sorry, yeah, quarterly. Okay, this is not the, I'm sorry, this is the, just, this is the simple interest form, I'm sorry. Not the compounded continuous thing. So it's compounded quarterly. So the quarters right there is 4, and that same thing also goes up here. All right, now notice that when we put everything in there, now the 4 into the 0.08 gives us 0.02. We add the 1, and we get 0.02. And then that's raised to the 4th p power. So what we want to solve for is in the exponent now. So we got to get that rascal out of there. So we're going to use ln. Like I said, ln is the most useful one for this. First of all, before we move on to that, divide both sides by 1,000. And that's where that 3.6 comes from right there, okay? Because this is like, you're kind of treating this almost like the whole thing here is an action, trying to isolate it. So that's why you divide by 1,000. So that all you have is the 1.02 to the 4t power. All right. And then we can just use the ln to do it. We take the ln of both sides. Okay. And then we take use the power rule, bring the 4t down to multiply. There's the variable now in a more respectable place that we can easily access. And let me kind of show you over here what's going on the board. Because I got a feeling that everyone might not be seeing that. All right. Four T. All right. So what we want to keep is the T, okay? So this is just like if so what we're doing is these things right here are the coefficients, all right? The T is the only thing. So what we're doing is we're dividing both sides by 4 ln of 1.02 in order to just leave the T by itself. And on this side, see, it's ln of over the stuff we just divided by. I should put it there. But so that's what we're doing, okay? Just in case you needed some fill in the blanks. Divide both sides by 4 ln 1.02, and it takes everything out on the right hand side except for that T, which is what we want to do always in equation solving is isolate the T. And then again, let's say 1.02 ln. I always like to show people what's happening here if I can. That times 4, and I'm going to stick it in 8, and I'm going to do 3.6 ln 16.2. So it take about 16, a little over 16 years to get to $3,600. You know, $1,000, and of course, this is a time when interest rates were actually about 3 times what they are now. All right, so this is another one. This is a pretty simple one here. The percentage of adult height attained by a girl who is X years old can be modeled by f of x equals 65 by plus 35 times the logarithm of x minus 4, and x represents the girl's age from 5 to 15. At what age does a girl attain 97% of her adult height? Now, we looked at something like this in a more simple case earlier with exponents, but we weren't looking for the percent. We were saying at what age, I believe. So we just fill in the blank, 62 plus 35 times logarithm of x minus 4. And what we're doing here is we're subtracting 62, okay? 97 minus 62 to get it away from here so that we just have numbers there. And over here is that clump of things that are multiplied. All right. Divide both sides by 35. They both divide by 35. So 35 divided by this side just leaves us with log x minus 4. 35 divided by 35 is 1. And then from there on, it's really a breeze because we're going to rewrite it as an exponential equation. Because this is log base 10, common log, 10 to the first power is equal to x minus 4. And so then we just add 4 to both sides, x is equal to 14. So at age 14, the girl has attained 97.
So any log base will be 10, correct?
What's that? If there's no number down there and it says LOG, then it means 10. That's the common logarithm.
Okay.
And thankfully, for the natural log, they've got a totally different one that's unique, the LN. And like I said, those are the two most important ones to use because those are the ones that are generally on the calculator. Now, if you got one of those fancy calculators, there may be something buried deep in the bowels of the calculator where you can do different bases, but for the most part, ever since I've been around studying math, there's only been log and natural log. And at one point, like in back in textbooks before they were calculators were popular, they would have like natural log and log values in the back of the book. So that's probably how this comes about. But I don't know if there's a calculator that does the other one. But if there's nothing there and it says LOG, then it means base 10. All right, so let's try to knock some of these off. We're getting a little short on time, but let's do a couple of. Let's solve. Okay, so this is like the very first examples we looked at. This one is base 5. So what we need to do if we want to use that first property, we want to see if we can rewrite this with base 5, and we can.
5 cubed on the other side.
Okay, so now that the bases are the same, then we can just do away with them and write the exponents equal one another. And then it's a real easy equation to solve. Divide both sides by 3. X is equal to 4/3. Okay. All right, let's see. I think I got one more like this kind of. This is the easiest one that I don't know if I'll spend too much on them, but at the time on, I think the other one's more important, but 9 to the x is equal to. All right, so as it stands, there's not a whole lot we can do, but if we can rewrite this on the right-hand side as three to the negative 1/3 power. All right. Well, we're still not helped yet, but what about this right here, that 9? That's actually 3 squared, right? So we can do a little bit of manipulation to get the same basis. So this would be 3 to the 2x is equal to 3 to the negative 1/3. And with a little manipulation, we got the same base on both sides. So we can solve 2x is equal to negative 1/3. So then divide both sides by 2. And then we take the reciprocal and multiply. So this is negative 1/6. Let's see. Let's look at one of the other types. This was actually, this is number 18 in the vector book. All right, so I'm going to look at number 26. Okay, e to the x is equal to 0 All right, so what I'm going to do, because it's got the base e, I'm going to ln it. And remember, this is the logarithm that's the inverse of the e exponent, okay? So these two things undo one another. But I got to do the same thing over here. So this is going to be just x, because these undo one another. That's e base e. Oops. X. And if you hit the calculator, you can see what that is. 0.83. Negative 0.186. So that's an approximation. Always watch what they're asking you to round off to. So when you take your value out of your calculator, round it off then. Don't round off before. Especially in like I teach statistics. And one of the biggest issues over there, because almost everything is an approximation. You're never dealing with any exact values over there. Almost everything is an approximation. So you have to look at what you're being asked to round off to. But you only round off at the end. Before you get to the end, you have the values out a couple of places past what you want. Because once you round off, you can never get that accuracy back. basically gonna look at the ones here, using the method, because the applications are pretty easy to set up usually. And use whatever method works. Let's look. I can do an application if need be. Let's do number 40. I got here, I know here, probably keep it busy for another half hour, but you know, I'm gonna keep going after it. That's gonna make sure I got enough. Keep it busy. Okay, here's one where we got base 3 to the x divided by 7, or 1/7 x is equal to 0.2. All right, so we're going to use the ln here. And this was going to be a little bit more entailed because, but it's an exponential problem, so we're going to ln both sides of it. All right, now this comes out in front using the power rule. All right. Now, remember, that's 1/7 x, okay? So we want to just get a plain x. So what we're going to do is we're going to multiply both sides of this equation by 7. If I multiply here by 7, or 7/1, see, I lose those x's, I mean, the 7's, and I just have a plain old x. ln of 3. But on the right-hand side, there you go, I've got 7 times ln 0.2. And then I can just evaluate that. Well, I'm sorry, divide both sides by ln 3. So x is equal to 7 yeah, this is going to be the last one that
Why we didn't take the ln from that side?
what's that?
Why we didn't take the ln from off the other side? We just leave it like that? From the 7 ln 0.2 and then ln over 3? Is it because it's not the same?
No, because what we're doing here is we're just using the ln. There's no properties being used here like I think you're thinking about. We're using ln on both sides. That's a legal move. But we're not using like putting anything together or combining anything.
Okay,
So with this ln on both sides, like I said, then we're using the power rule to bring that out in front. Then we're doing an equation type move. In other words, we're multiplying by 7 to get the x alone. And then we got one more step to get the x alone, which is divide by ln 3. So here, that's just 1. So we just got a plain old x. So like I said, is if you go in and do this real quick, so you can get it. So 3 ln, put it in, and then 0.2 ln times 7 divided by the ln of 3, And we've got negative 10.254. Again, you gotta watch what's asked for. I don't have the book open. Oh, I'll have enough time, because I have a long, I'm not sure we'll be able to do two more. Let's see. All right, let's just look at the logarithm equation. And that'll probably be enough. This one is it's all right. Now we got a logarithm equation, and we're going to use some of the properties to help us get that x out of there. All right, now remember, the E and the LXN are the same. And so we can do this. We can go backwards. Remember how we were taking the power out of the exponent and set them in? Well, let's put them back in there, in the exponent. So E to the ln of x plus 4 is equal to e to the 1, all right? Both, they have the same basis now, okay? Same basis, so we can write, well, first of all, the e undoes this thing right here. And I should have mentioned that. We're not just doing the taking the, we could go that direction, but then we get back where we're at. So what we're doing now, we did go backwards, but now this E undoes the ln. So we're left with square root of x plus 4 is equal to a single power of E, and it's going to write it as E now. All right, so now, how can we solve that? Well, this is something that we had, and we have it in 9.7, one of the last things that we go over. In order to get that x out of that root, we got to square this. Square both sides. Which means this is going to pop out. And then one more little move. So this is going to be x is equal to e squared minus 4. All right. I got one more. I said it's kind of long because this is one of the ones you have to check. Let me just show you real quick. I'll set it up and I'll move it real quick. Because this one's going to have to involve putting things together. With the power rule, not power rule, the product rule. Okay, we're going to use the product rule on this. So what we got is log 2x minus 1 is equal to log of 3 times x plus 3. So that's going to mean log of 2x minus 1. And I'm just going to run that 3 through. Distribute 3x plus 9. All right, so now we're using that property, that one-to-one property, so that we can simply solve 2x minus 1 is equal to 3x plus 9. So if you go through and solve it, I'm going to do it real quick. You get x is equal to negative 10. All right, but in the check, when we put over here log, and you're going to have to just do it on one side to see. It'll do it to all onto this one too. So what's going to happen is you got log of negative 21. And if you try to evaluate that, of course, that's going to be not going to work. So we got to throw out, so there's no solution. Same thing would happen on the other side too, just to show you. So if we put negative 10 in there, negative 10 plus 3 would be negative 7. And that's not going to work either, because it's got to be positive. All right, so that's it. Let's squeeze that one in. All right, if you got any questions, let me know.